bulk manufacturing. What is bulk manufacturing and how we are producing this? Just that it's a removal of material in a bulk, isn't it? So there are two methods, that is wet etching or dry etching, and there we have discussed about this different plane orientation and the application of different plane orientation for what? For anisotropic etching, because isotropic etching is we are not able to control that etching, so we are using most of the cases that is anisotropic etching. So how this plane are going to affect the anisotropic etching? When we are using different orientation plane, as different planes crystals, silicon crystals have different rate of etching, and isn't it? So we are controlling the etching with the by using different plane of orientation. For example, if we are using in this case, if you are using a crystal or a substrate that has that surface coincide with the plane 100, and we want to control the depth of etching. So at what depth whatever we want to hello, is this okay? It's okay, no issue. So the at the where and what at what depth we want to get each this to get a particular shape, so that accordingly we will use the other plane like 1 1 1 plane after that certain depth of 100 plane orientation crystals, so that in this way we are able to use the going different plane orientation to control the etching rate. So we have discussed about this one, what is wet etching and what are the types of anisotropic etchants. And we can see here in the table also that the rate of the etching decreases with the change in the material, like silicon is crystal or silicon substrate with 100 plane have a etching rate of around 0.25, and with the etchant, with the same etchant, when we see with the silicon dioxide, the rate is around 40 to 80, and we can see another times like silicon nitride with the same etchant, so the rate is different. So we can see that the etching rate is different for the different types of silicon rate with the same etchant. So here you can see that the silicon dioxide with KOH is almost 1000 times slower than with the silicon, and the silicon nitride is another order. So there is a term that is selective ratio of a material. Selective ratio of a material, that is the ratio of the etching rate of silicon by the etching rate of material, that we want to calculate the selective ratio. So the silicon dioxide has the selective ratio of 10 to the power 3 with KOH, and the silicon nitride with the is of another lattice 10 to the power 4. This is the selective ratio, and the selective ratio is what? Etching rate of silicon, that is silicon substrate, and to the etching rate of that material. That material in case of silicon dioxide is the etching rate of silicon dioxide material with the same etchant. The thing is with the same etchant. So the main theme is that higher the selective ratio, the better the mask material is. If you want to make a silicon dioxide mask for a silicon substrate, then we need to find the selective ratio, which material has highest selective ratio and what is the application. So according to the selective ratio, we are able to say that this have the highest selective ratio, so this is the better material for the mask. So we have also discussed about the etching geometry, how the etching rate and again affected, or there is some defect like under etching or under cutting. So we have discussed about that, how to control this on the etching geometry. and we have discussed about like how to control like each stop. We're going to using each stop, and one of the method is by controlled by doping, and the another method is controlled by chemical each stop. So we have discussed that we will provide in the doping case we dope the silicon substrate with either p type or n type, and the next method is the electrochemical each stop.